brain modes, and we've taken an exciting journey from diving into mathematical principles of dynamics on the first day, modeling the moving brain through neuroimaging and electroencephalography. And today we shift towards examining the translational potentials of these computational models. So it's my great pleasure to introduce today's speaker, Professor Christoph Mathys at the Interacting Mind Center, Aarhus University. Christoph got his PhD in Zurich at the ETH and University of Zurich, working with Klaas and Stefan, the same supervisor. That's a time when I was in Zurich as well. Exciting time developing the HGF. Christoph also did his postdoc with Carl shortly thereafter. So many of you might know Christoph as the inventor and developer of the hierarchical Gaussian filter, the HGF, which has been used in computational psychiatry in numerous applications to investigate maladaptive beliefs and learning under uncertainty. Essentially a model that investigates the dynamics of learning, the slow and fast aspects of learning under uncertainty. And I was trying to count this morning how many papers have used the HGF in the last 5 years, and it was like 30, or I don't know. I stopped around 30 and I wasn't sure. Yeah, but there's a lot of papers applying this method. So many of you know him for the HGF. I also know him as a great friend and actually officiator of my wedding. Many of you might not know that. and a fellow fan of Larry David and Curb Your Enthusiasm, which but don't worry, you don't have to curb your enthusiasm for the talk. Let's give Christoph a warm welcome.
Okay, we're off to a blazing start here. So I call my talk Change of Mind for the simple reason that that gives you an easy excuse if you change anything about the title or the abstract, but I actually am not going to use that excuse. I'm going to do exactly as announced. So I will talk a bit about the clinical computational challenge facing us when we look at maladaptive changes in beliefs, which appear in many psychiatric disorders and which we'd like to model computationally. And that's not always easy. And I'm going to show you some of the approaches we have tried. Looking at the clinical side, we can say that psychotic experiences are thought to emerge from various interrelated patterns of disrupted belief updating. And these patterns can be, for example, overestimating the reliability of sensory information, misjudging task volatility, or misclassifying the cause of an observation. Now, bringing all of these phenomena into one modeling framework is a challenge. So these are all kinds of aberrant inference that form the substrate of psychotic experiences. And we would like to have computational approaches, because that is also the motto of brain modes, that sort of simplify this and break it down into its main components, its main modes. And I'm going to try and work out a few of these commonalities that we see in very different domains of the modeling of psychiatric disorders. So all of these phenomena relate to the adaptation of beliefs. So probabilistic predictions guiding actions. So what we have, or what we're trying to build here, is models of precision-guided belief updates. So I will show an example of a published study using generalized hierarchical Gaussian filtering. That's a tool and framework which enables arbitrarily large networks of nodes coupled not only by their variance, but also by their means. I'll show a simple example of this in a nice study in the field of computational psychiatry. This is a solution in the continuous realm. So you have a quantity, and this quantity is somewhere, and you want to place it in that continuum, on that manifold. So the question is, where is something? That can be an abstract quantity, like a probability. Is the probability low or is it high? But it can be anything between 0 and 1. Different tools are needed in the categorical realm. So when the question is, what is something? But there is a conceptual relation between these concepts. And that is, at least, there are more connections, but at least by the role played by precision in guiding belief updates. So in both realms, we find an important role for precision in belief updates. So models of categorical inference are crucial for understanding delusions. And this is what I'll finish on. So a bit more on where and what. Many of you, most of you, all of you probably are familiar with the where and what pathways of how information is processed in the brain. So goes to the top of the brain when the question is where, and goes to the temporal lobes when it's about what. And we see a similar distinction conceptually computational. So as we navigate the world that changes around us, we need to adapt our beliefs. And this has both a where and a what aspect. And on the where side, we need to track how things move in space, again, the continuous realm. And on the what side, we have the categorical realm. So we need to categorize events into such that have the same explanation and such that have a different explanation. These explanations are causes, so we have to make causal attributions. And that is where delusions come in, where events are attributed to causes in a maladaptive way. So let me first turn to the where side. And I'll give you an example of a study that was published this year. This is in the broader field of computational phenotyping. So we're estimating individual parameters that provide a trait-like characterization of the underlying computational patterns in the individuals we're looking at. And these may have the potential to guide psychiatric treatment. We, for that purpose, in this study, introduce a novel hierarchical Bayesian model that describes how individuals simultaneously update their beliefs about task volatility and noise of the observation. And we use this generalized hierarchical Gaussian filtering to do that. We apply the model to data from a modified predictive inference task in a test-retest study with healthy volunteers, 45 people, 4 sessions where they were measured repeatedly. And we examined the relationship between model parameters and schizotypal traits in a larger online sample with 437 participants, and in a cohort of patients with schizophrenia with 100 participants. So there are basically 3 parts of this. This was published in Biological Psychiatry, and this is work together with Mathys, who is a postdoc in my group, and Klaus Lamm, who is a professor at the University of Vienna. The task that people were asked to do was very simple. There was a cover story, but let's dispense with the cover story. Basically, they had to track the location of an outcome, and this outcome was noisy. So basically, it was on a continuum here from 0 to 100, and somewhere here, the outcomes, the green dots came. And here, the dots are orange because we're in a different phase. We had a low variance phase and a high variance phase, then again a low variance phase, and then again a high variance phase. And that basically means there's lots of noise in the high variance phases, and there is much less noise in the low variance phase. The outcomes were drawn from a Gaussian, and the variance refers to the variance of that Gaussian. Also, the mean of that Gaussian could jump from time to time at unexpected times for the individuals. And the task was simply to predict where the next observation would happen. And there were 160 trials. And there was a good reason for 160 trials, and I'll show you that. So the computational problem that the participant has to solve here is they have to make a decision as to what the prediction error that they observe between what they predicted and what actually happened, what that is due to. And there are 2 possibilities. The first is that the prediction error is noise. So I, as the participant, can adjust my predictions, but that wouldn't help because it's just noise what creates my prediction errors. So that wouldn't help to reduce future prediction errors. I might even make them worse. So if I start overfitting, start trying to fit the noise. But there's another possibility B. My prediction errors reflect the change in my environment. So the mean has jumped. The mean is in a new place. And adjusting my predictions will now help to reduce future prediction errors. And this is not just a binary decision. So I can sort of allocate part of my prediction error to A and another part of my prediction error to B. I have to find the right way to divide that up. So this can be a combination of both. And if it's a combination, how much of A and of B is there? So in a nice picture, we have here the unobservable true state, which I have to make a prediction on the basis of what is observable. So I make an observation after having made a prediction, and then I get an outcome, and that gives me a prediction error. And now, sort of the Bayesian description of what I do with this is depicted here on the left. So the rational thing to do here is to calculate precision weights on this prediction error and make a corresponding update to my belief about where the mean sits at now. And our hierarchical Gaussian filtering model gives us an approximation to this Bayesian inference task that works very efficiently with one-step update equations. But basically, I need to have beliefs about where the mean is, what the variance of the observation is, and what the volatility of that mean is. So how likely is it to change? How quickly does it change? How does it jump around? And that's all the components that go into my belief update. So I have a belief about the volatility, I have an uncertainty about where it is, and I have a belief about the outcome precision. And all of that flows into my update. And that is how I adjust my learning rate here, because this weight on the prediction error can be interpreted as a learning rate. Now, this all drops out of the variational inversion of the generative model of the hierarchical Gaussian filter here. So people often speak of the hierarchical Gaussian filter, but it's actually a family of models. And in the generalized hierarchical Gaussian filtering approach, we have lots of nodes that we can connect in many different ways. So what we have here are 3 HGF nodes. These are 3 quantities that move with time in their own space, and they are coupled via their volatilities. You can see the XV showing up here in the equation for the X. So this is coupled via the variance, via the volatility. And here you can see in the U, the XT is also, the XA, sorry, is coupled via the volatility. And this is the volatility of the volatility. But we can also have mean coupling, and we can have nonlinear couplings, and we can build models of arbitrary size like this. And we have a simple algorithm that tells us what the update equations need to be with an arbitrarily sized model. So the update equations are basically there for free. And this now allows us to, sorry, that's all there is on this slide, to infer the belief trajectories of one particular participant here. This is an example of one participant. This is how this participant's belief about where the mean is evolves according to our model, the model you saw on the page before, on the slide before. And this is how this participant believes the volatility evolves. So you can see the input noise evolves. The volatility is down here. So with the input noise, you can see it actually is learned. So in the low noise phase here, we have a pretty stable estimate. Then in the high noise phase, the fact that the noise has increased is learned. We go back to the low noise phase, and the noise estimate actually comes down and then goes up again in the high noise phase. And the hardest part to estimate, because it's highest up in the model hierarchy, is the belief on the volatility. You can see that it takes a first jump when the mean jumps for the first time. Then, quite appropriately, it only increases very slightly when the noise increases. So this is actually appropriate that the noise estimate here rises, whereas the volatility estimate stays more or less constant. The second time, a bit more of the attribution goes to an increase in volatility, but also appropriately, the noise estimate goes up here. So this is this trade-off that the agent has to make between, is it an increase in the volatility, or is it a change in the noise of the observations? So this dividing up this of the attribution of the prediction error between the two possibilities, A and B. So the plan for our study was first to do a simulation study. So we wanted to know whether the parameters that we estimate for each participant and that tell us what the model's estimate of these belief trajectories are they stable? So if we take the same participant this week and have them come back next week, will the parameter estimates hold up? So that is the first thing we wanted to do. After doing it in a simulation study, we did with an actual test, in an actual retest study in healthy volunteers. And then experiment number 2, replicate and extend experiment 1 in a larger sample of healthy participants, and experiment 3, extend to a data set of patients with schizophrenia. So this is the simulation of the parameter recovery, and this is how we hit upon using 160 trials. You can see that at different noise levels, the different parameters. I'm sorry, somehow the translation to Windows didn't work here. So these are the 3 parameters that we're estimating. This is the omega for the tonic volatility of X. This is the theta of the, which is the tonic volatility of the volatility at the highest level. This is the hardest to estimate parameter. And this one here on the right is the omega of the input noise. So you can see some parameters are easier to recover and others are harder to recover. But from about 160 trials, you get a well recoverable parameter for each of these, as long as the input noise or the noisiness in the decision making of the agent that we simulate isn't too high. That's how we hit upon 160 trials. In the paper, you can see another simulation for a task with binary outcomes. And there you can see you have to take 480 trials at least, and even then the recovery isn't as good as it is here. So this is a strong argument in favor of using continuous outcomes instead of binary outcomes, because when your participant only makes a binary decision, yes or no, left or right, or black or white, then there's only one bit of information in that decision. Whereas here, where people make a prediction on a continuum, there's much more information in every participant response. So we need fewer participant responses to get well recoverable parameter estimates. Good. So in the experiment 1, predictive inference task, as I explained, sessions were at least 1 week apart. We had 45 participants. Performance was rewarded, and both mean and standard deviation of sampling distributions changed randomly. The Peters delusion inventory was acquired in the 3rd session. And this is what we found regarding the reliability of our estimates. This is the interclass correlation for the 3 parameters. And they basically follow the pattern that we saw in the recovery. So the omega here is the one that holds up best in the interclass correlation, theta a bit less, and omega about like theta. These are not stellar values, but they are sort of an indication of how much we can expect parameters in these computational phenotyping studies to replicate here. The raw parameter values are a bit harder to get to correlate between different sessions than derived parameters here. So we have quantities that relate to the prediction errors, psi1, mu alpha, mu v, that recover much better. And then if we look at how the relation holds up in different participants between confidence and prediction error, between updates and prediction errors, and between learning rates, and so empirically observed learning rates derived from the predictions they make and the outcomes they receive, how that correlates with the variance estimated with the model. This is very highly recoverable from session to session in participants. So these are very good ways computationally to phenotype our participants. So, and these are how the measures that you saw in the last slide relate to the individual parameters. So they correlate appreciably well. Then we also see sort of an out of task validation where we also applied the two-step task to the same participants, and we can see that the parameter theta that we estimate has a relation with the points earned on the two-step task. Now, how does it all hang together with delusional ideation, with what we measure in the Peters delusional inventory? And we can see that we see a connection in theta. That there is also somewhat of a connection in omega alpha. I don't want to make a big distinction between significant and non-significant differences, but you can see a pattern here. And the important thing is this pattern replicates. You will see the same pattern again in experiment 2 and experiment 3, which are totally different data sets, also slightly different tasks and so on. And here you can see this relation depicted between theta here and the Peters delusional inventory score. Then we also see a difference in behavior in that people with high Peters delusion inventory tend not to lose confidence after getting a change point in the trajectory of the task. So when the volatility changes, when the mean changes, variance, then people with low Peters delusion inventory scores tend to adjust their confidence downwards. So they realize, oh, something's amiss here. I don't understand this task environment at the moment. I have to learn again to get my confidence up. And the same thing does not happen with people who score highly in the Peters delusion inventory. So let us turn to experiment 2. This is a reanalysis of the data published by Claire Gilliam's group a few years back. This was an online study of hundreds of participants. The task is very similar, but not exactly the same as in experiment 1. And they also acquired lots of psychometrics. Here you can see the familiar pattern again. Theta correlates positively with the outcomes that we measure. In our case, it was the Peters delusion inventory. Here, schizopathy, unusual experiences, subscale. So these are comparable measures. They are a bit, they relate to how people interpret, or how sort of delusionally people interpret their environment. But also on the introvertive anhedonia subscale, now we see connections between scoring on this scale and the parameters omega and omega alpha that we acquire here. And again, we see on the schizopathy scale, we see the same pattern that we saw before. Trials after change point, we see a difference in how people adjust their confidence there. And again, people that score highly on schizopathy are more confident even after changes. Experiment 3 is a reanalysis of data from Michael J. Frank's group. And here, the participants were patients with a diagnosis of schizophrenia or schizoaffective disorder, 100 participants. These are stable outpatients, most of them on antipsychotic medication. There were 2 sessions of the predictive inference task, a bit shorter version than we had, but 2 sessions, differing in an appetitive variant and an aversive variant, where people try to either win reward or avoid loss. Positive symptoms were rated using the brief psychiatric rating scale, and negative symptoms were assessed with the scale for the assessment of negative symptoms. We see the same parameter again in the positive symptoms, which is also relates to the same things that the Peters delusion inventory picks up, and measure we have in experiment 2. We again see the exact same pattern in the parameter estimates in how they relate to scoring on this. And we see again the same pattern that we had in the study before in the loss avoiding condition with the negative symptoms, and that also corresponds nicely with the schizotropy, introvertive, anhedonia subscale. Good. And here again, the connection of theta with the positive symptoms and the theta with the negative symptoms. Because these were two different GLMs on the in one condition and in the other. So for the reward seeking and the loss avoiding, we also analyzed everything together in one canonical correlation analysis, and these associations hold up when we analyze everything together and not and don't divide this into two different GLMs. A few remarks before I turn to the what path. This was still in the continuous realm, everything. And we're going to stay in the continuous realm for a few remarks about generalized hierarchical Gaussian filtering before we turn to the what realm, the categorical realm. So as I already mentioned, generalized hierarchical Gaussian filtering allows you to build networks of arbitrary sizes and connect them via either value coupling or volatility coupling. And in value coupling, so when the two nodes are coupled by the mean, so one node pushes around the mean of the other node, these couplings can be nonlinear, so you can use a ReLU or saturation coupling or whatever catches your fancy. Nonlinear coupling can be any function which is twice continuously differential, almost everywhere. So the ReLU is an example. And this removes previous limitations on, for example, Dirichlet categorical models that we used to have. Much of this, or most of this, is the work of Lilian Weber. This was part of her PhD thesis, and the paper is basically soon going to come out. There's a preprint up to now. Then all of this has been implemented in software. So we have the old MATLAB toolbox that doesn't allow for generalized hierarchical Gaussian filtering, doesn't allow for making these nodes in a simple and intuitive way. Of course, you can go and you can program it in. But in the new tools we have, hierarchical Gaussian filtering.jl, a Julia package being the first one, you can do this in a easy and organic way. Implements generalized hierarchical Gaussian filtering and has a sister package called action models to have your response models and model how the agent that you're modeling uses its beliefs to perform actions. Both are part of the computational psychiatry GitHub organization, which is run by the TNU in Zurich. And parameter estimation here is done via Turing, which is a powerful general purpose sampler. And this allows for hierarchical parameter estimation. So if you have a study where you have a patient group, you have a control group, and you want to estimate parameters not just at the individual level, but at the group level too, and then at the population level at the top, or you have a between subject design where you have a drug condition, a placebo condition, and so on. You can build that into the your whole analysis organically now and use Turing to estimate these parameters at all levels. And the most common HDF models are pre-implemented for convenience. This was mostly the work of Peter Testrapode, my PhD student, who will graduate in about a month's time, and again, Lillian Weber, who delivered the concepts behind it. But then, this is also available in Python. So we have PyHDF, and this basically does the same that hierarchical Gaussian filtering.jl does in Julia. Again, the most common models are pre-implemented for convenience. And here, the work was done by Nicolas Legrand, a former postdoc in my group. Now let us turn for the rest of the talk to the what path. This is mostly a teaser. We don't have any experimental studies on this yet. We published a generative framework for the study of delusions in 2022 with Tore Erdmann, former PhD student of mine. And the main idea there was that if I have a series of causes that I know of, so the blue cause here, depicted for convenience as a Gaussian, and the, what is that, cyan, and the green one, these are all different causes. And when I now make an observation, like the black dot here, I have to attribute that observation to a cause. I have to say, well, you know, I hear a sound, and what is it? Maybe an engine misfiring, or maybe a gunshot, or whatever. I have to classify the observation and attribute it to a cause. And of course, sometimes the observation is a bit outside of the expected. And all causes are only noisily observed, so they all have a range of outcomes that can be attributed to them. So what do we do if we have an observation that lies a bit outside? Well, one thing we can do is we can say, this is something we haven't seen before. This needs its own causal explanation. We come up with a new explanation. And we have this little red Gaussian here as a new observation. However, alternatively, and especially if the observation is closer to a known cause, what we do is we adjust our known explanation a bit. So we say, oh, okay, so this must have been an engine misfiring. I didn't know that a misfiring engine could sound exactly like that, but I'm just going to broaden my idea of what it sounds like when an engine misfires. So I'm not going to say, oh, probably the Martians landed and set off I don't know, an explosion. Similar to this, what guided our thinking was you can get a series of observations like this one, and you can say, well, this is just a range that one explanation could take. So you have these observations, and you say, yeah, they all come from the same source. And what inspired this was case reports of Capgras delusion, where Capgras patients believe that someone close to them has been replaced by an imposter. So it's usually the wife or someone else who's close, who still looks the same, behaves the same, speaks the same, but the patient is convinced she is an imposter. She is not really his wife. She is someone impersonating his wife. And it was found that one could show such patients. I don't think it works with every one of these patients, but there are cases where one can show them photographs of the same person from different angles. And they will say, these are different people. So they causally attribute two different underlying causes. even though healthy people would say, well, this is the same person, but just photographed from different angles. So the computational equivalent to that would be to take the exact same observations as here that fall in a certain range, but say that, was that a sign for me? No, no, okay. But attribute the same observations to different causes. We went about modeling that using a particular extension, hierarchical extension of Dirichlet process mixture models. And we found that we could model the protection of a central belief, which is an important phenomenon in delusions, using this approach. So we start out with this belief, this one cause that our agent believes in. We equip the agent with a parameter mu tau that we model to be low first, or we simulate in the first simulation, our agent has a low mu t. Now, what is mu t? Mu t is the expectation of the precision of an explanation. So we have an agent that tolerates explanations that aren't very precise. And when we show this agent a series of outcomes, it attributes many of the observations to its one known cause. And for the rest, it comes up with different causes, but not very many of them, because it is tolerant of broad explanations. If we do the same thing, and the only thing in this simulation that we changed is the expectation on the precision of an explanation. When we do this with an agent that wants very precise explanations, what we see is that the central belief is highly protected. And we have all these little ad hoc explanations for all the other observations. So this is a phenomenon that we can call explaining away. And that is what delusional people do. Whenever something happens that contradicts their delusion, they come up with an ad hoc way to explain that away. This work is now being continued by a current PhD student, Christopher, who has built on this framework, come up with a modeling strategy that even involves hierarchical Gaussian filters. I didn't tell him to do that. He did it by himself. So I thought we could do without hierarchical Gaussian filters in this realm, but apparently we can't. And what he found is that this bears explaining in some detail, that when agents learn in an environment that is very highly ambiguous and are then placed in an environment that is rather unambiguous, they take their style of inference with them. And that style was actually good, optimal in an ambiguous environment. But now that they're in an unambiguous environment, it becomes delusional. And we can show this in this simulation here. So what do we have here? This is a heat map of mean adjusted RAND indexes across 10,000 simulations. What is the RAND index? The RAND index tells you how well two ways of clustering the same data correspond to each other. A RAND index of 1 means the two clusterings are exactly the same. And a RAND index, so this is a mean adjusted RAND index, the mean adjusted RAND index of 0 tells you it's basically chance whether a given observation is in the same cluster in the two different clusterings. So it's a similarity measure for clustering solutions. The perfect agent column here is just for illustration. This is for comparison. The perfect agent is the one who knows the parameter of the simulation. So it does make mistakes because the simulation is noisy, but it knows the ground truth parameters from which the simulation is made. Sigma is the difference in precision, actually the difference in log precisions between environment and agent expectations. So what you can see here is 0 is a perfect match between the environment and the agent's expectation of the precision. This is the same parameter again as in the previous slides. And here, the agent expects less precision than the environment actually has. And here on the left, the agent expects more precision than the environment actually has. And here in the vertical axis, we have the difference between the means, and that is basically just the ambiguity of the environment. So large difference between means means little ambiguity. So these are unambiguous environments, whereas down here we have ambiguous environments. And the line of numbers here indicates the optimal, the best place of the clustering solution. And you can see that in highly ambiguous environments, you will do a better job of clustering. This is the surprising result down here. So what you see down in this area here, or even it starts up here, you would expect, or at least I would expect, the numbers to go straight down. So when you have a match with your environment, then you are best. But that turns out not to be the case. In an ambiguous environment, you will do a better job of causal attribution if you expect too much precision. That means if you have a delusional style of inference. And now what happens if you take an agent that was trained in an environment like here and learns to cluster by overestimating the precision, because that gives the best results in such an environment. You transfer him to an unambiguous environment, then he will develop this delusional style of inference. So the key observation is that in ambiguous environments, causal attribution works better with higher expected precision. And I mean, with sort of unmatched higher expected precision, and not just matching the environment. So you expect higher precision than you would expect to be optimal there. Now my slides have stopped advancing. Oh, here we are. It took a long time. So this is what we did here. So we have a matched sigma agent here on the right. So this is an example with very low ambiguity, 6 standard deviations between the means. So we're at the top of the heat map here now. But the agents have been trained differently, and they have a different sigma here. So no, they have been trained the same, but they have a different sigma. So all of them have been trained for, I think, 100 episodes, and then they are tested for 60 episodes. And these are the 60 episodes. You know, here we went longer because we want the phenomenon to arise here on the left. That's where I draw your attention. On the left, you see what you can describe as a delusion emerging. So there's nothing there. The actual causes are shaded red here. There's nothing there, but because of the inherent randomness of the observations, all of the agents initially believed there could be something here. And you can see the agent with the matched sigma, the one sort of who's been trained in an unambiguous environment, deals gracefully with this. So the delusion sort of disappears quickly after a few observations again, whereas in the lower sigma agents, the ones who basically are down here and have learned to expect too high precision matched to the environment. In these, the delusion here on the left persists much longer. You can see in between, I don't know how to stop this, but when you look at basically snapshots of this, there are always times where here it's totally, the belief has totally disappeared, whereas here it's staying. Good. This is what I have. Thank you.